Hi guys, today we will be discussing the problem number 6.11 from the textbook HIbbeler. From the textbook Mechanics of Solid by HIbbeler R. So I think it's the 14th edition, if I am correct. So this is actually a problem uh, regarding the shear force and the bending moment diagram. So I'll just read out the problem. So they draw the shear force and bending moment diagrams for the pipe. The end screw is subjected to a horizontal force of 5 kilonewton. Okay, so let me draw this particular. Give me a moment. This is B, this is A. It's 400 mm as they have mentioned, and a 5 kilonewton is being applied. Okay, so I hope that is clear to everyone. So here, what we have to, how do we tackle this problem? So in order to tackle this problem, we need to um, first make free body diagrams. Okay, free body diagrams, obviously. So let me make the free body diagram here. 5 kilonewton is being applied. Okay, and here there will be RA. Okay, and let me just consider this as a single body here, and here there will be RYZ and RXZ in X and Y direction. So here I have only given Y direction force at A because this is a rolling contact, okay, roller over there, not rolling contact. So there is a roller over here, so it will only give restriction in the normal direction. That is this RA. Okay, so 400 mm in mm. Okay, everything is in mm. Here it was 80 mm. Okay, so the question is to draw the shear force and bending moment diagram. Let me draw the shear force and bending moment diagram. So let me ask you, what is RYZ? So as we can see from the free body diagram, that if we solve the equilibrium of forces in y direction, then it will be RYZ minus RA is equal to 0. Okay, RYZ equal to RA. Fine. RXC, how do we get? By solving the equilibrium equation in x direction, whereby RXC minus 5 is equal to 0, RXC is equal to 5. Okay, so here what we have to look into is um, you just replace these numbers, sorry, the letters with the values. Okay, right now. Okay, 5. Okay, that is clear. So we have got unknown RYC. Okay, so in order to find this unknown, we have to use the moment equilibrium. Okay, so let me just bring these things. Okay. So I'll just choose the moment equilibrium about this particular point. Okay, C. Sigma mc is equal to 0. So how do I write? RA, I'm considering anti-clockwise to be positive. So RA into 400 minus 5 into, this was 80. Okay, so into 80 is equal to 0. So RA becomes 1 kilonewton. Okay, you have to be very particular with the new units. So we have got RA is equal to 1 kilonewton. Thereby RYZ is also 1 kilonewton. I hope that is clear to everyone. So we will just replace that. So here it is 1, here it is 5, this is 5, this is 1. Okay, these are in kilonewtons. So next, what we have to do is um, we have to move these forces 1 and 5 to this particular point. Okay, B. So how do we do that? We know that at C, at this particular point C, the forces are 1 and 5 here. We have to use the principle of transmissibility and see whether there is any additional effects. So if you consider 1 Newton, okay, so this 1 Newton is acting on C in the y direction, and this line of action is coinciding with B, so there won't be any moment, any external moment acting upon B due to this 1 Newton. So we can just write 1 Newton here. But what about 5 kilonewton? It is acting at 80 mm. So that will produce a force as well as moment, which is equal to 4. 80 into 5, that is 400 kilonewton meter. Kilonewton mm. So 400 kilonewton mm. So that will be 400 Newton meter. Okay, I'm converting, or let it be 400 Newton meter. Okay, so I am writing this as 400 mm. I have got 5 kilonewton here, 5 kilonewton here, 1 kilonewton here, 1 kilonewton here. Okay, so now I have to. So this is an important figure. So upon this particular free body diagram, new free body diagram, we will create the shear force as well as bending moment diagram. So this I will just copy. Okay, and I will just keep this here, and let me mark this as A and B. Okay, so the pipe is AB. So what about shear force diagram? Let me just draw a line. Let me draw a line. Straight line. Okay, almost a straight line. Okay, okay. So this is AB. Fine. I think I made a mistake. Wait a minute. I'll just rub this off. This big line. So AB I have got. So at this point A, what is the shear force? Let me say that this 1 Newton is acting downwards, isn't it? So I'm considering that let me say how I'm going to consider the positive negative shear forces. Okay, this is positive shear forces. So if I okay, so this is considered to be positive. On the right hand side it is going downwards, on the left hand side it is going upwards, and this is the configuration. Why this is in this configuration is because of the principle of, because of the concept of complementary stresses. I hope that is clear to you, because it has to be in equilibrium, right? So the shear forces has to be in this direction. This is in this direction, the space has to experience the shear force in this direction, and accordingly the other both the directions. So here I have considered this as positive, okay, for the shear force. Shear force. So on the right hand side, if it is downwards, then it is positive. On the left hand side, if it is upward, it is also positive. Okay. So here it's another direction. On the point B, it's upwards. Okay. So I'm starting from point B. So it is, since it is upwards, I have taken -1 Newton. Okay. And it's constant throughout, isn't it? There is no other shear forces. And at a downwards force is acting. Okay. If I am drawing it like this, fine. So this is negative. So this is the shear force diagram. What about the bending force diagram? Bending moment diagram, sorry, bending moment diagram. So if I consider the bending moment diagram, the bending moment is considered to be positive if it is sagging. Okay, but this is hogging. Okay, this is hogging, which will hog and result in this deformed shape. So this is negative, and opposite to this is sagging. So here, since it is hogging, I consider this is, so what was this value of the bending moment? It was 400 Newton meter. Okay, this is minus 400 Newton meter. And what about in the cross section? At the cross section of this, any cross section at x, what will be the bending moment? Will it be same as minus 400, or will it be different uh, from minus 400? As you can see that these shear force is 1 kilonewton, which is acting at B, will produce a shear force. Okay, so let me just write that over here. So at any x, this is x's, any x's which is in x distance from the B will have a bending moment of minus 400 is always already there, and 1 kilonewton is in a sagging, sagging direction. So 1, since I have wrote this particular unit in Newton, I'm writing this as Newton. 1 kilonewton is 1000 Newton into x. Okay, this is minus 400 plus 1000 x. And this x has to be in meter, since I have wrote this as meter. So how is it going to be? Minus 400 plus 1000 x. So it is going to be linearly varying. Okay, doesn't look like linear, but it is linear. Okay, since I'm very bad at drawing, let me just make it much easier for you. I'll just use this. Okay, it would be something like this. Okay, so this is the bending moment diagram, BMD. I hope you enjoyed the session. Thank you.